So let K be a finite extension of the p-adic rationals. You could take K equals QP. And let A be a ZP algebra. So ZP is the ring of integers in the p-adic rationals. And by a p-adic Galois representation, I simply mean a representation of the form which maps the absolute Galois group of K continuously into the some GL D of K. So modular some equivalence. So I'm saying that there's an action of this Galois group on a free A module of rank D, and this equivalence is just saying you can change bases and write different matrices. Okay, so this is my p-adic Galois representation, and what would a family of such look like? An algebraic family of such representations look like. So for instance, maybe we can write this Galois group in a short exact sequence that looks like this. So okay, here is the Galois group. It has an inertia subgroup. So this is the inertia, which is the kernel of the map to the Galois group of K sep over K, where this is the residue field of K. And this group is isomorphic to Z hat, which is the profinite completion of Z. And here 1 corresponds to the Frobenius element. So maybe we could look at a representation that goes something like this. We have the Galois group mapping to this Z hat, mapping to this GL1 of, let's say we're looking at mod P representations. So let's say this is going to GL1 of FP bar. And maybe 1, the Frobenius element is going to some A, which lives inside finite extension of FP. So maybe it lives inside FQ cross. And so this map is really factoring through Z mod Q minus 1, which is the cardinality of this set. And this is how this representation looks like. In a family, we might want to vary this A, right? So we could try, so we could try something like, maybe we want to say that there should be a family which essentially sends this Z hat to, instead of A, we want a variable, an invertible unit. So maybe we want to send it to something in this string where 1 should go to X, but this doesn't work. This doesn't work because this is a profinite group. This has to be a continuous map. This has discrete topology. And the image has to be finite. This is a compact group. And there's just no way to extend this to Z hat. Right? So this doesn't work. So maybe the issue is that this exact sequence, well, maybe instead of looking at the entire Galois group, we should look at the pre-image of Z inside this Galois group. And then we are removing the topology part of Z hat. And then we can work with the representations we get for this. The pre-image is called WK. And we can look at this. Okay, well, we can do something slightly better. In fact, the inertia group has a quotient, which is also topologically finitely generated and profinite. So it ends up posing similar issues as a Z hat. So maybe we could also decomplete it and discretize it and work with that. Great, we do get some reasonable families, but there's sort of two facts related to those families which can be improved upon. One is the geometry ends up being really rather weird. And the second is that the study of p-adic Galois representations has suggested the possibility that you might be able to get irreducible representations as specializations of reducible representations. So what I'm saying is that if you have a representation of the Galois group of K bar K, and it's a reducible representation, so let's say it looks like this. So this is this gives an Galois invariant subspace. It seems that there might be a way to specialize, to construct families of these which specialize to an irreducible representation. So there is no way you have such an invariant subspace of the Galois of this representation. And so we are led to consider what are called phi-gamma modules. So actually the Etale, what are called Etale phi-gamma modules. So what are they? Very quickly. Can I erase this? Or no?
Yeah, you're on the line.
Okay. So what's the deal with phi-gamma modules? So if you have your field K and you have the algebraic closure of K which lives over it, you could break up this tower with some highly widely ramified extension of K infinity. So you could get this by adjoin all p power roots of unity. One. So something that's highly ramified, and it sits between K bar and K. And now let's just call this Galois group gamma. And this Galois group has a really interesting property. This turns out to be isomorphic. So this is characteristic 0, but this turns out to be isomorphic to the Galois group of a characteristic P field. So this is the theorem of Fontaine and Winton-Berger. Sorry. And it so turns out that representations of this group are somewhat more reasonable to classify, and we can use that to classify these representations through this isomorphism. And so what do we get? Well, it's Galois, K bar, K infinity reps are sort of like something called Etale phi-modules. So this phi is related to the Frobenius in this Galois group. And this is really some linear algebraic data. It's encapsulated by a few matrices, which give this phi action on whatever this module is. And I put this in quotes because this is an equivalence of categories when the coefficient ring A, the representations, is a finite ZP algebra, then this is true. This is an equivalence of categories, and otherwise it may not be.
Finite means as a set or as a
module. Yeah. So for instance, A could be ZP and A could be FP. Okay, so this is some progress. Now, another thing you could do is, okay, so let's see what we've done here. This entire Galois group is now being understood via this phi action. And this Galois group, this turns out to be isomorphic to something like ZP. And this is now topologically generated by one element or so, and this is a widely ramified part. So we've really simplified the Galois group quite a bit here, in some sense. And what you could do to get at full Galois group action, you could add some gamma descent data here, and you could get phi gamma modules here. And so, okay, so we have a way of writing down the representations of the full Galois group, which are described in relatively very sparse data. And these turn out to really these turn out to have this property that if you write these families of reducible representations, you can specialize to irreducible representations. So that's really nice. You get these quite big families. Okay, so what's the deal with this? Why do we care? Well, we care for many, many reasons, but let me give one reason. So one significance is that there exists a conjecture by Emerton-Hellman. Oh, by the way, I'm so sorry. So I should say here that this, so we can define a stack XD over spiff of ZP, which is the formal spectrum of ZP, which basically means the test objects are p-adically complete ZP algebras. So they could be FP, they could be a discrete valuation ring over ZP. And this is the stack of modular stack of Etale phi gamma modules with coefficients in whatever your test object is. And and this stack is called the Emerton-G stack because it was studied by Emerton-G in the book. Okay, so one significance of this stack is that there exists a conjecture by Emerton-G and Hellman that there exists a functor, a fully faithful functor from the category of some GL2K representations. So I am omitting some terms that go here: smooth, derived category, bounded, finite represented cohomology, something, to coherent sheaves on XT. And this functor is supposed to encapsulate the burgeoning p-adic program, and it satisfies a bunch of conditions which are inspired or which are motivated from Taylor-Wiles patching methods that have been used for a while. So I won't say anything about that, but essentially the point is that this XT is the setting of a p-adic correspondence. And let me just state a couple of very seemingly random facts about XT, and then I'll say something about what I did in my thesis. So if you look at, let's put D equals 2. So if you look at the reduced part of X2, so this is, you're taking the reduced part, which means you have to cut out all the formal directions in spiff ZP in particular. So this is going to be defined over FP. So this is an algebraic stack of dimension equals the dimension of K over QP. And it's a finite presentation, or it's finite type over F. And what that means is that smooth locally, it looks like finite type schemes over F. And it has irreducible components. So irreducible components of this space X2 reduced and one-to-one bijection with the irreducible representations of GL2 of OK, which is the ring of integers of K with FP coefficients or FP bar coefficients. So we have sigma corresponding to, let's say, X sigma. And the way this correspondence works, first of all, it's suggestive of Langlands, because you have this relationship between GL2, some representation theory of GL2, and some irreducible components of this moduli stack of Galois representations. But the way this correspondence works is actually in a way that you look at some dense set of points, you obtain some numerical data from it, from the way the inertial group acts, and then you compare it to some discrete data associated to these things, and then you match them up. But maybe a better way to think about this is that one expects that if you look at the sigma, this is a GL2 OK representation, you could make it a GL2K representation by compactly inducing. And then you can apply this functor to it, if it exists. And once you do, its support is, okay, so support is X sigma for most sigma. So for what I call non-Steinberg sigma. So for most of these irreducible representations, this labeling is really quite reasonable if this p-adic Langlands thing exists. This is specific to GL2, by the way. In general, the constraints, you have to put more conditions on sigma. So now, what do we have? So in my thesis, I show that if sigma and tau are not isomorphic, and also this non-Steinberg thing, so non-Steinberg, then the extension group of sigma and tau as GL2 OK modules, the first extension group, this is non-zero, then this implies that X sigma and X tau intersect in codimension 1. Oh, so this is codimension 1. The converse of this has counterexamples, but if you put suitable genericity conditions on sigma and tau, then this becomes an equivalence. So this is one of the results. And I think I'll stop here.
Question.
Are these the Emerton G stacks known to have some sort of finiteness properties for general D?
So these are a priori just in algebraic stacks.
Right.
And beyond that, you know.
Okay, so but maybe for D equals 2, we know more.
It's still just an end algebraic stack.
Oh, even for D equals 2, you have to somehow cut it off.
Yeah, yeah. I mean, if you were
You have
to
to cut off by the determinant or something, if the minimum.
Oh, I don't know that. I mean, in the sense that, okay, so if they had a dimension theory, then it would correspond to the dimension of the deformation rings, which is finite, but there is no dimension theory.
Is the situation better for semi-simple representation? Is there the geometry easier? Or
Can you repeat the question again? Sorry.
Is the geometric situation better for classes of semi-simple representation?
I'm sure the answer is yes, but I don't know what it looks like.
In the intuitive picture, the use that VL2 is its own Langlands dual.
I mean, I'm using that in this formulation of the p-adic Langlands correspondence. Otherwise, there should be a dual group in this picture. So yes, I use it entirely here. Yeah.
So how does this problem of having an extraneous deformation get solved here?
Which one?
You said that you would want to see some deformation from an irreducible representation to from a reducible one to an irreducible one?
Yes.
How does it?
So it just turns out that when you write the phi-module, it has all of these specializations. I mean, even the it's sort of related to, if you look at the classical story of studying p-adic Galois representations, it turns out you can classify the decrease of those representations with some something on a p-adic disk, and as the valuation varies, you are getting all sorts of the reductions look very different, and that's exactly the kind of picture that's being got in the phi structure. But I don't know if I can say anything more satisfactory, this is unsatisfactory. Yeah.
I guess.
Yeah.
More question.
So is the theorem something that is predicted by this conjecture?
Partially. So for instance, the support of this sheaf should be X sigma. So certainly, and this is a fully faithful functor. So any extension theory of these sheaves should be visible on the supports. And so if the support is empty, then certainly you would expect there to not be any extension there. But the extension one is a little bit more stringent. The fact that it's codimension 1 is a little bit more stringent, And it turns out that if you were to do patching with these things, the Taylor-Wise patching suggests that these sheaves should actually be locally free on their support for generic irreducible components. And generic irreducible components are also smooth. And so you could do some kind of commutative algebra there to see that those two, the extension should capture that. But a lot of the part, maybe some of the interest in this theorem should come from the fact that this also covers all non-generic cases. And yeah, for which it is not entirely clear what the picture is for these sheaves.
All right, thanks.